Hello, beautiful ones. Today we are going to talk about transition elements. Now, the question is, what are transition elements? Transition elements are elements whose atoms have a partially filled d orbital. A partially filled d orbital in one sense. You will recall that d orbital can take maximum number of 10 electrons. This is called fully filled. Now, if we have D1, D2, if we have D1, D2, D3, D4, D5, D7 to 9, they are partially filled. When an element has any of these d orbital, it is referred to as transition elements. We have the 3D series, 4D series, 5D series, and the 6D series. And why can't we have 1D series of the transition elements? This is it. The first shell can only take s electron, while second shell will take sp, the third shell will take spd, the fourth shell will take spdf, the fifth shell will take spdf, the sixth shell spd, and so on. Now, in the first shell, there is absence of d orbital. In the second shell, there is absence of d orbital. Now look at the third shell, we have the d orbital. That is why it is starting from 3D series. Then the 4D series means the elements in which the electrons are ending in the fourth shell, d orbitals of the fourth shell, while 5D series will be the elements in which the electron ends in the d orbital of the fifth shell. That is how we got to know 3D, 4D, 5D, and 6D. Now, how do we fill in their electronic configuration? We have this S in the first shell, SP in the second shell, SPD in the third shell, SPDF in the fourth shell. In the fifth shell as well, we have SPDF and the rest. Now we have 1S. 1S means S in the first shell, followed by 2S, 2P, meaning in the second shell we can see S and P. That is why we can never have 1P. The reason why we writing 1P here will be very wrong, because there is no P electrons. There is no P, because there is no P orbital in the first. In the have 1S, 2S, 2P, S in third shell, P in third shell, D in third shell. This is it, and so on. Now, using the Hofbann's principle, you trace this diagonally. Having a diagonal line, yeah. Then we have this. Using these traces, we have our first traces is the 1S. Our second diagonal trace is 2S. Then the next trace is 2P, 3s. We have it as 2p 3s. After this, we go to the next diagonal line. We have 3p 4s. Then we take the 3d 4p 5s. Followed by 4d 5p 6s. After this, we have the next line, 4f 5d 6p 7s. Then we have 5f 6d. This is how to fill in the electronic configuration of each element. Let's take that of scandium 21. Now, using this Hofbau's principle of filling electrons, we have our 1s first. You have 1s. Remember that s can only take 2 electrons, p can take 4 electrons. That is, let me have it somewhere here. S will take the maximum of 2, P will take the maximum of 6, D will take the maximum of 10, while F will take the maximum of 14. Now we have 1s. Since S can take the maximum of 2, we have it like 1s2, 2s2, followed by 2p, P will take the maximum of 6. Remember, we are going to d orbital, the 3d series. So when we get here, we'll stop. We have the 3s orbital, 3s2, 3p6, then we have the 4s2. Now we have 3d. How do we know the total number of electrons in this d? We count what we have on ground. 2 plus 2 plus 6 plus 2 plus 6 plus 2 will give us 20. 20 minus 21, we are left with 1. Yes, we have 3d 1, which is showing a partially filled d orbital. That is, the d orbital is only having 1 out of 10 electrons. Same thing you do for that of titanium. Titanium being 22, we have the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then here we have 2 left. We have it as 3d2. In continuation of our electronic configuration, I have my scandium to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d1. These can be written as AR, so that we have 4s2, 3d1 left. How do I get my AR? AR is a short form for argon. Argon is a 3p series with complete electronic configuration. Like argon has 18 electrons. Now, by the time we sum up the 1s2, 2s2, 2p6, 3s2, and 3p6, by the time we sum it up, it is giving us 18 electrons. That is the configuration of argon. Therefore, we can maximize our time by writing AR for scandium, then 4s2, 3d1. This representing this. In continuation, we have our scandium to be scandium 4s2 3d1, titanium Ar 4s2 3d2, vanadium Ar 4s2 3d3. Now our chromium should have been Ar 4s2 3d4, but this is wrong. Why? This is because there is stability in empty filled, half filled or fully filled d orbitals. D orbitals are more stable when they are empty filled, half filled or fully filled. Empty filled such that we have D0. Then half filled such that we have D5, that is the half of the total electrons that D can take, which is 10. And fully filled such that we have D10. Now, because chromium is closer to attaining a more stability, that is, chromium is close to attaining its stability. Instead of this, it will prefer taking 4s1 3d5 data so that chromium becomes more stable. So this is the configuration for chromium. For manganese will now be Ar. Manganese will not take 4s1 3d6. In order to attain stability as well, s orbital is occupied by 2 first, then we have 3d5. Therefore, manganese and chromium are both stable. Then, considering the next being iron, we have our Ar 4s2 3d6, and the nickel becomes Ar 4s2 3d8. Now, the case of copper should be 4s2 3d9, but because it is closer to attaining the stability, it will become 4s1 3d10. And for zinc, we have Ar 4s2 3d10. For the stable compounds, we have chromium, manganese, copper, and zinc. Through the electronic configuration, we get to know that chromium, manganese, copper, and zinc are the most stable 3D elements because they could attain the half-filled and the fully filled d orbital. But note that zinc is not a transition element. Why?